So I sort of love this juxtaposition because I think we've just heard a whole lot of talks that basically said how today we can learn a lot more about ourselves. A lot of what we're learning about with all of this is things about humanity and people. And what I'm going to talk about a lot is learning about things outside ourselves, in particular, what's really out there in the universe, and trying to actually distill our observations away from that as much as possible to sort of turn into what's really there. And I also kind of love talking about it in this space because, again, I think there's this interesting juxtaposition about this modern era and this room and sort of where we sit with respect to that. And sort of what we're trying to do is understand the world around us, and that's taking us deeper and deeper into technology, as we'll see a little bit. So there's, as I said, there's two themes to the book. It says how physics and scientific thinking illuminate the universe and the modern world. And part of, obviously this is a short talk and I can only give a flavor of it, but part of what I'll be talking about what we're learning about today, but also I really do think that thinking in a scientific way is incredibly important in today's era. So this is just a random picture. You should just note that, in case you haven't figured out where it is, but the icons there that I want you to notice are the Eiffel Tower and the kiosk with a poster on it, because both those will come back later. One of them will come back in this slide, where what I want you to think about when we look at that Eiffel Tower, and this again relates to the theme of us versus the world, is just what we're seeing depends very much on how we view things, what our resolution is, what the scale at which we look at things would be. Obviously, we look from an airplane, we don't see the we don't see or hear the Eiffel Tower. And if we look really closely, we see the amazing iron gridwork that's in it. And if we look even closer, of course, we would see the atoms or whatever that it's composed of. So what's out there in reality, a lot of the time, I think people genuinely get confused by what we see, what we observe in our daily lives, and what is really fundamentally out there. And that's the goal of science, is to go beyond the sort of obvious that we just see in our everyday lives and really find out what's there at both larger and at smaller scales. And this is what I was just saying. I think our intuition, in particular, is guided very much by what we observe. And so are our physical theories in the beginning. But as we observe more, then we can have physical theories that are toned to the different scales that we can then observe. And of course, what's important to keep in mind is that the things that we have intuition for are really a very small range relative to the scales of the universe. It's something like a millimeter to a kilometer. Whereas I'll give you a very brief tour of the universe to say the scales that we can study with science, and physics in particular, mostly. So first, let's think about large scales. So let's start with the scale of the known universe, which is 10 to the 27th meters, 100 billion light years across. Now, why do we give it a finite size? Well, that's because the lifetime of the universe that we know about is finite, and the speed of light is finite. So that doesn't mean that the universe is actually finite in size. It means the part that we have a hope of seeing, observing, detecting is finite in size. Now, within that, that's still a very enormous scale. And within that scale, of course, we have all sorts of different objects. I don't have time to go into all of them. But we have galaxies 10 to the 20th meters across. We have solar system, the Earth. And I'm putting a human in to scale this. We're the scale of about a meter. It's not a coincidence that the unit of measure is the meter and everything else is done relative to the meter, because that's a very human scale. It's about the size of a human being, the size of an arm or something. So that's a scale that we're familiar with, but we have these many different scales, of course, out there in the universe. The one thing that I do want you to observe about this is that what's really interesting is that even though it's an enormous range of scales, we're pretty much using the same laws of physics across all those scales. We're using Einstein's laws of gravity, but we're even using Newton's laws of gravity a lot of the time. We're using standard laws of electromagnetism. The rules of physics aren't changing as we have these different scales. Now let's contrast that to small scales, which is actually what's mostly being studied at the Large Hadron Collider, which I'll come to, which is some of the most interesting research going on today. But small scales, notice the human is at the top now, so the meter is the biggest scale on this graph. really, as we go inside, we keep discovering new phenomena, new mechanisms. That's not true just in physics. That was true as true in biology years ago. I mean, we didn't know about the circulatory system until animals and people were cut open and arteries and veins were discovered. We didn't know about red blood cells until we could look under a microscope and see them. We don't know about DNA until we could use X-ray diffraction or X-ray technology to really find out what's there. So we can conjecture what exists on these scales that are invisible to the human eye, but really until we develop the tools to go in and look inside, we don't find them. And that was true also, of course, in the world of physics. When we finally had tools to explore smaller scales, people discovered the atom. They discovered the atom wasn't the smallest object. There's a nucleus with electrons surrounding it. The electrons, as far as we know, as far as we've observed so far, seem to be fundamental particles, indivisible. But that's not true of the nucleus, which in turn has more fundamental objects known as quarks, which are held together through the strong nuclear force mediated by particles called gluons, which are like photons that mediate electromagnetism, but they mediate the strong force. So again, these are things we wouldn't have found without looking. But on top of that, quantum mechanics was discovered when the atom was understood. It was in the process of trying to understand the atom that quantum mechanics was developed. And no one would have conjectured quantum mechanics unless there was experimental evidence leading us there. Its premises are so counterintuitive, so counter to what we see on a daily basis. Yet, it's what underlies everything that we know about. And now we're continuing to look inside. We have now what's called the standard model of particle physics. It describes particles like the electron and the quarks that I just mentioned, and the forces through which these particles interact. And we're trying to understand, is there some underlying structure here? Are there some underlying principles? And I'll tell you a little bit about the questions that we believe should be answered today. And today, they should be answered at this machine known as the Large Hadron Collider. It's probably one of the worst names out there, but it is accurate. It's large. That's 10 to the 27th kilometer underground ring. This picture is supposed to illustrate that it's underground. It's hadrons. It refers to protons. It's actually protons that are being collided. Protons are in this category of particles called hadrons, and they are colliding. And I'll tell you a little bit more about that. The other thing I want you to recognize is that this is certainly not the smallest scale that we can hope to study with experiments. There are much, much smaller scales. And we can go down 16 orders of magnitude, and we'll probably get to another paradigm shift at the same level of the shift to quantum mechanics, known as quantum gravity, where there'll be a theory that describes both quantum mechanics and gravity. It's probably not going to be explored at the energies and distances we're looking at today. Yet, in the process of answering those questions, we might get some insights into more fundamental structure. So as I said, this is the frontier energy and distance. And just to put in perspective again, it's 10 to the minus 19th meters. That is the distance. That is an incredibly small distance. We have no imagination, we have no sort of intuition, I should say, for what can be happening on those scales. Yet, with advances in technology, we can now probe inside and see what is going on at these very tiny distance scales, which is also known, we measure energy in very funny units, is also known as the tera-electron volt scale. And this is what's going on there. This is just the machine itself, the Large Hadron Collider. Those protons are getting accelerated by going around a ring 11,000 times a second. They go through this tunnel. I just visited the tunnel the other day. It's kind of fun to see all the technology going on there, the magnets that keep it in the tunnel. And then these protons collide inside a detector. So there's the Large Hadron Collider, which is the machine, and these are the protons colliding inside one of the general purpose detectors known as ATLAS. There are two general purpose detectors known as ATLAS and CMS, and that is where the actual physics is done, where the protons collide and then they come out and we learn what is happening. And I'll tell you a little bit more later. But I do want to point out this machine is quite amazing. It is a remarkable achievement. And it really is about as distant in some ways from the kind of technology that we've been hearing about as it can be, because we're going to a scale as far as possible from sort of human scales at this point. And furthermore, we're looking for fundamental structure. At the scales we're familiar with, all this fundamental structure leads into this tabletop, this people, and all these networks we've been hearing about. But at the fundamental level, we hope the laws of physics are simple enough that we can deduce what's going on in the most fundamental structure. And that's what we're looking for. So it's sort of the opposite goal. We're not trying to understand how everything fits together. We're trying to understand what is at the core of matter. And it takes an amazing reach of technology. This is the limit of technology. This is the smallest distance that technology can take us to. The way it gets to small distances is by going to the highest energies achievable today. This machine is 7 times the energy of the machine that was just turned off in the United States, known as the Hadron. It also has what's called the highest luminosity, the highest intensity. That is to say, there's a huge number of collisions a second, billions of collisions a second. And to get that, we need technology that is incredibly amazing to see. And that's one of the reasons I do theoretical physics. I don't do experimental physics. I predict what we should find there and what they should be looking for. But it is kind of impressive to visit this machine because at this point, it really is a miracle of technology. It's the coldest extended region that exists. It's 1.9 degrees above absolute zero. And just to put that in context, that's colder than outer space. And there's an extended region that is this cold. That's to get the superconducting magnet technology. It's the biggest, most effective vacuum that's out there. It has to be extremely devoid of atoms. The reason for that is, first of all, you don't want spurious collisions to happen. And also, it's to keep things superconducting. It has the strongest magnets in production. Just as an aside, those magnets actually do end up having uses. Some of the magnet technology goes into MRI machines and elsewhere. And it has a huge amount of energy in that. The reasons for those extremes, or as I said, is to collide together enormously energetic protons and focus that energy in as small a size as possible. It's much smaller than the size of the proton itself, and to get as many collisions as you can, because we're looking for very rare processes that happen maybe 1 in a trillion times. And the goal is to measure these results with these efficient and sensitive detectors. They really are quite impressive because one of the things that it's hard to convey here is it's really enormous, but it's not just enormous, it's like the size of the Notre Dame. But it's also measuring things incredibly precisely at this micron level to really see what is there at the core of matter. So here's what happens when they actually collide. They collide and then it goes through the different layers of the detector. And those detectors are designed to measure as much as we can, as precisely as possible. What is the charge? What is the energy? What is the momentum? And then, when they find what comes out, what has to be done is to deduce what was there in the first place. And like I said, most of the time, that will be ordinary, what we call standard model particles, stuff that we know exists. This is something called the Z boson, which is a particle like a photon that communicates the weak force. But what we're looking for is the new stuff. What is it that hasn't been found yet? And what is that? Well, what do we hope to learn here? Well, there's some really interesting questions, and this is the right energy to look at those questions. One is how elementary particles acquire their mass. That has to do with the search for the Higgs boson. You might have heard about that in December when it got a lot of news because there was some announcement made showing some hints of the Higgs boson. The question is, how do these particles get their mass? That sounds like a really strange question because you probably think particles have masses from the get-go. It turns out that if that were the case, you would find ridiculous predictions in your theory. Energies of collisions greater than 1, probabilities greater than 1. So we know that's not the case. We know there's something deep and fundamental that underlies the standard model, and that has to do with this Higgs mechanism and the Higgs boson that's being searched for. And this is a good year because we should actually be able to pinpoint whether that particle exists within the year. They're upping the energy a little bit and they'll have 4 times as much data. So we'll know the answer to that question. The other question that's really very basic is what explains the weakness of gravity? Another way of asking that question is what sets the masses of elementary particles? Again, this might sound like a really abstract question, but by learning about this, we actually hope to learn more about the nature of space and time. It turns out this is a really tough question to answer. And some of the answers involve notions like extensions of space-time symmetry into the quantum regime, something known as supersymmetry, which is being searched for, or something as exotic as an extra dimension of space, something I talked about a little bit the last time I was here at DLD. And I've done some work on both of these topics. And another thing we hope to learn, possibly, is about the nature of dark matter. I wish I had more time to tell you more about all of this. But let me just give you a sense of how we're finding it. And how do we look for an extra dimension? That sounds like an incredible thing to do at a particle collider. But it turns out there are particular particles that happen only if there are extra dimensions. So protons can collide together and produce something called a Kaluza-Klein particle, a particle that travels in the extra dimension. It has momentum associated with another dimension of space, a dimension of space beyond the three we're familiar with. It would actually decay, in our theory, according to our theory, it would actually decay just like a Z boson did inside the detector. So by finding the decay products, one can go back and reconstruct what was there, find out, is this Kaluza-Klein particle really there? Is there really an extra dimension of space? And that's actually one of the searches they're doing right now. So just generally speaking, just because it is such a different endeavor, our goals today are really to go beyond the established theories, to keep doing what we've done as we've gone inside matter and see not just what are the particles that are there, but is there really some fundamental new paradigm that we're missing? Like I said, we've discovered how the body works. We discovered quantum mechanics. Can we discover something really basic and new about the nature of space and time even, or the nature of forces? We want to make discoveries that can't be explained within the current framework and use experiments to choose among the potential underlying theories. And I talk a lot about how we go about figuring out what is likely to be found there and how we would know about it. And so just as I said, there's sort of two themes to the book, and I just want to basically change modes momentarily just to say that these are some very big questions. And I think, again, it's interesting the contrast between what we heard earlier today and this, because I think in both cases we're basically up against the fact that there's this enormous amount of information out there. In the case of social media and social networks and the internet, it's a lot of information that's readily accessible. In the case of the universe, it's actually information that's hard to get. And so you need this amazing technology to try to probe these scales and get to these scales where we can get this information and try to piece it all together. And in both cases, you're trying to sift out what's really interesting from all the junk that's out there. You're trying to find, are there underlying principles by which you can make sense of all of this? That's what we as humans are trying to do. We're trying to find some order in this universe. And I think one word that I talk about is the sublime, which I think captures this a lot. The sublime is sort of something that's beautiful, but it's also scary, and sort of its accessibility, but also its distance from us. And I think one of the reasons, especially in the United States, you find such controversy and such heated arguments is people use very different approaches because people are at the same time fascinated but also scared. And I think basically art, religion, and science are all ways we try to get at these very big questions. And as you might guess, I think science is probably going to be the one that actually moves us forward. But the other ones, I think, are ways that we as human beings try to grapple with these big questions. So two of the questions I talk about in my book are both, how do these methods differ and why do we care so much? So I think we mostly know what science is, but I will give a Sherlock Holmes quote, which says, "Detection is or ought to be an exact science and should be treated in the same cold and unemotional manner." So I think I think the unemotional part is kind of true, but I think the cold part is why science gets a bad name. But I think it doesn't have to have this bad name. It's still this fascination that we as human beings have in being able to access and understand these scales that seem, at first sight, so distant from where we can go. The fact is, all these tools and all these theories allow us to really get at these scales that in principle seem so scary and distant. One thing to keep in mind, and I think is often forgotten, especially when we're talking about this kind of physics, is that the ingredients and the macroscopic phenomena can be different. And again, we saw that with the networks. I mean, the networks are what we see in a network phenomena is very different from what's at those individual nodes. And that's true for physical theories as well. We're looking for the fundamental ingredients, but that doesn't necessarily explain everything. And sometimes people get mad about that. They're thinking, you're saying that you're explaining everything. We're not explaining everything. We're finding out what are those basic ingredients of which everything is made. And I like to think of music as more than just this oscillation in our ear. But defining what that is a very challenging question. Yet, you need that oscillation in order to have music. These physical correlates are essential. So getting at what's out there and underneath is important. And the other lesson, I think, that we've seen over the years is that these scales that seem so distant at some point become so essential later on. I mean, quantum mechanics seem pretty irrelevant to our daily lives, yet it was the basis of the semiconductor industry and the electronics, of which basically most of the stuff that's going on at this conference is based on. So this fundamental physics doesn't have an immediate application, but certainly in the long run has an amazing influence, both in the way we live our lives, but also just in how we think about the universe. I just have a couple more. And I think one of the biggest difference with religion, which I'm not going to spend too much time talking about now, is that science relies on these physical correlates, whereas I think in many ways religion leaves that out. They sort of have this magical way that these ideas come to us, but they forget that these physical correlates are essential. And again, for lack of time, I'm not going to go into it. And art, I'd say, is more about how we as human beings perceive it, how we interact with it. I think it's incredibly important. It's not science. It's definitely subjective, but it's a way to communicate. And the last time I was here at DLD, I actually talked with a composer, Hector Parra, and an artist, Matthew Ritchie, about a project we were actually conceiving at the time, which actually came to fruition. It was an opera project that premiered at the Pompidou Center and then went on to Barcelona Opera House in Luxembourg and Brussels. So I'll just briefly show you that it actually happened. Here's some samples from it, which you cannot hear, apparently. Well, there would be sound if there was sound. It's actually an opera. There's a CD. But this actually did premiere. And part of it was to convey this notion of discovery and also creativity that permeates both the art world and the science world. And this was exploring an extra dimension and showing, using that as both as real and as a metaphor for how we are exploring the universe. So this was a joke about that transparency I showed you in the beginning with the Eiffel Tower and the affiche. The affiche on the kiosk, the poster on the kiosk, was actually an advertisement for an opera, for our opera, which is why it was there. So again, there were sort of two themes that I wanted to get across. What we're exploring today, both at the Large Hadron Collider and dark matter, but also what goes into scientific thinking and why. I mean, if you follow American politics, you can see the frustration that we as scientists have with sort of the way things are being handled and why these different ways of thinking are so important to understand. So I'd say that we've really understood an incredible amount about both the universe and the small scales, but we have a long way to go and a lot to learn, and that's what we're doing today. So thank you.